Okay, so it's week 11, this is lecture 22. We have finished the wind chapter. Our next chapter is going to be wave energy, and then we'll get into geothermal. I guess in some ways we're jumping the gun a little bit on putting geothermal into summary 4 since we haven't covered it yet. But what I want to go over is how you compare the two economically, and again, I know summary 3 can be a challenge. Have you guys finished summary 3 though? It's not as big a deal for 102. You've kind of been through it once, so I'm not so for 102 you should be in good shape. But what I do want to do is cover the economics for summary 4, and then maybe if we have time at the end, I'll start to take a look at summary 5. In the past, I've done this information entropy thing for summary 5. I'm leaning a little bit more towards doing an integration model, and I'll show you why. And I'll show you something I'm working on right now, and there is an economic spreadsheet in there, and we'll sort of use that as a launching point for the economic spreadsheet comparing a wind versus a geothermal. But so where I'm going with that is with the final chapter being on integration and the summary 5 that I've been doing in the past being on kind of a more, I don't want to call it philosophical, it's very real. I mean, the paper that I've put out there in the past is something I've been working on for a long time. It's sort of the other bookend to that first paper you read in 101, kind of the energy density paper. The last paper I had for 102 is this entropy and information and money paper. So maybe it's not that bad of a choice, but on the other hand, I think a lot of where we're going to see our numerous energy technologies going is towards some kind of integration. I mean, already we're seeing CO2 being pumped out of Wyoming underground in Montana for advanced oil recovery. You sort of see these different energy technologies talking to each other. And what I'm going to show you here, we've got a downdraft wood-fired gasifier, this biomax system that we sent down to our collaborators at Bitterroot Valley Greens. So the wood, obviously, is a sustainable, renewable energy product. It makes CO2, which is good for greenhouses. It makes heat, which is good for greenhouses. It makes electricity, which you need to run an operation like that. And so there's your kind of integration. All the parts kind of fit together into really a big recycling loop, if you will. Because when it comes down to it, that 10 million to 1 ratio problem that we did, we're consuming fossil fuels 10 million times faster, and I went over this in recycling tech a little bit today. It's not sustainable. There's no cycle there. It's just a plunge to the bottom. So moving forward, what we're going to have to do if we're going to sustain our civilization at its comfort level and energy consumption level is figure out something that's cyclical, something that happens on a more regular daily or annual basis. But anyway, let me show you this proposal. I'll show you some of the economics there. We can get into a little case study comparing two different technologies, and then like I said, if we have time, we'll get into summary 5 since we're done with chapter 7. Okay. And this is a proposal that I almost submitted last summer. It was due at 5 p.m. in Washington, D.C. We submitted at 3:15 p.m. in Montana, which apparently is 5:15 in Washington. It wasn't evaluated. So when the professor's homework doesn't get turned in on time, it does not get graded. We'll just put it that way. As it turns out, though, we might even be barking up the wrong tree with this particular funding opportunity. I sat down with one of the directors at the USDA, and he said the RFP, so the request for proposals, was submitted, but then due to, wrangling in Washington, the funding got pulled, and they didn't have the money they expected to actually fund it. So anyway, this is a project that I've been very passionate about for a while now, almost a year, and I'll just show it to you as is. I've got another collaborator, and I think as you guys go through your careers, you'll start to see the value of having strong collaborators. If you're in a startup or classmates or marriage or relationship, whatever, it's good to have a good collaborator. So with this proposal, we have several renewable energy technology collaborators. So algae aquaculture, Bitterroot Valley Greens, that's the greenhouse I just mentioned. Blue Sky Stewardship, those guys are here in town working on their own greenhouse model. Bureau of Business and Economic Research, they're a little think tank at the U. Skyber Enterprises, that's Craig Thomas down the Bitterroot. Clear Sky Climate Solutions, this is Keegan Eisenstadt. He's an international carbon trader who lives here in Missoula, just lives up the hill from me. Department of Natural Resources and Conservation. The Evergreen Foundation, so these guys are kind of a Sierra Club for trees, the health of the forests, more or less. Food Energy Inc., this is a little spin-off from Algae Aquatech. Forest Business Network, again, how do you keep the forest healthy, sustainable, making money. Montana State University Extension, these guys are sort of the lab end of things. They're going to take the data, do the chemistry. Northwestern Energy, partnering with them on a grid tie scale system. This is Steve Running's group. He's a Nobel laureate here on campus. Pyramid Mountain Lumber, I don't know if you heard about them. They just got bought out by Weyerhaeuser, which, might be good for them, but a lot of the local economists say, it's not so good for the Montana economy. When these things sort of get bigger and bigger, they tend to push all the other smaller timber companies out of business. It's just kind of the law of scale. It's the same thing that Walmart does to the mom and pop Hallmark card shop downtown. Sustainable Business Council, it's a group downtown that really promotes businesses that try to hit that triple bottom line, people, prosperity, planet. Titan Machinery, these guys would be responsible for building some of the technologies. Triple W, this is the John Deere, again, sort of the tech end. And then the Zero Waste Group is a little group that I sit on here in Missoula trying to, get us off the landfill and all that good stuff. Okay, so the integration part, and this is kind of looking forward a little bit to the last chapter of the book. And what I've tried to do here, and if you guys ever find yourself in a grant writing job down the road, what I've tried to do is actually just take the language of the RFP itself, of the request for proposals. And I think I even have that. It's sitting right here. Okay, so yeah, so it's the Department of Energy and the USDA collaborating, more or less. They realize that energy and agriculture are intimately related. We submitted ours on July 27th, 5:15 p.m. So anyway, what I did, I more or less took, I highlighted the text, I more or less took the language straight out of here once I'd read the whole thing, tried to address really as much as we could each bullet point. Super competitive. I mean, if you look at that thing across the United States, if you add these two up, 4 to 20 awards across the whole country. So that it's me fighting with a few hundred other me's across the country for this pretty limited pot of money that, as it turns out, it wasn't even available. But anyway, you can't give up. There's your institution of higher education, private, blah blah blah. So we're right where we need to be on these guys. Anyway, so you follow the rules, submit the document, and here it is. Okay, so like I said, we got the 25 kilowatt biomass gasifier that makes electricity, woody biomass to energy and heat, grid tie, there's your Northwestern Energy, and what we're looking to do is even partner with coal-fired power plants to reduce the amount of pollution they put in the air. So there's even more integration. So you're actually using the woody biomass as a filter, so you're cleaning the air with it, more integration. Building upon algae aquaculture's existing systems, so integrating with them. Making biochar, which is for agriculture, for the USDA, making tar for a variety of other industries. There's some manufacturing, biofuels, and then we're going to do it both centralized versus decentralized, and I think you can appreciate the reason for that. So right now, we're sort of coming off of this model of centralized power production, going more towards decentralized. And so what makes sense the most, economic sense? I think we looked at that map of what the country might look like if we go to 100% renewables, and it's not like every single house is going to have a solar panel on it. It might be more economical to go and put the 3 megawatt system out on the edge of town and just, knock that thing out, and that way the PV happens faster, quicker, and we get going with renewables. But on the other hand, it might be better in the case of biofuels to do your processing out in the field rather than dragging the logs into town and spending a lot of energy moving mass around when you could have a product that you just make out in the field. Okay. Now, I'll just skim through the rest. I'll just kind of show you the pictures and the highlights. This thing's kind of long, but here's more integration. So, and remind me, I'll cover this when we get to chapter 10, but again, many different technologies sort of feeding off of each other. This is our prototype, showing we've already, built a portion of the system. This is our data, showing that our unit actually sequesters carbon dioxide. An example of responsible forestry, saving some of Teddy Roosevelt's cabins from burning down rather than just letting the firewood build up forever and smoke the place. Here's the greenhouse. So it needs electricity, it needs heat, it needs CO2. That's where the wood comes in. Here's how we integrate with a coal-fired power plant. Here's an example of how we've done some field demonstrations already, responsible forestry. Here's our team of collaborators, so showing we've got a technology, we've got data, we've got core, we've got coordination, we've got scaling. There's legal on here, there's economists on here. Everyone's got their little CV attached, how much money they're going to put in. Okay, and then a little timeline. And then now for the economics. So what I'd like you to do if your wind and your geothermal is have something that looks like this. It doesn't have to be completely rainbow colored like I've done, but just whatever works for you. So what I've shown here is that there are 20 million acres in Montana. There are 135 million, maybe as many as 150 million dry tons of biomass. In the case of your wind, you would say there's this much wind resource at 100 meters, I'm going to put in a 100-meter tower. Or there's this much resource at 60 meters, I'm going to put a 60-meter, whatever you happen to be. So this is your resource. Same thing with geothermal. We've got a ground temperature of X and this much heat. And I can show you how to do that. Here's your megajoules per ton. So how much, for a ton of lumber, how much energy is in it. This is how much you can move. And this would sort of, for your geothermal, this would sort of be how much heat you could pull out of the ground. So for a given amount of pumping, how many joules come out, and we can run that little number too, so it's not too daunting. Megajoules per load, BTUs per load, just putting in a different units, so all still units of energy. And now here comes the money part, right? So picking up and dropping off a container is going to cost you $150. It's going to be $325 to haul it because it's $3 per mile. You're going to run it for 100 miles, et cetera, et cetera. So these are your costs. And this is sort of the overall dollars per ton of processing. And just as a side note, we did this in recycling technology today, but we decided that my neighbor, instead of turning his 13 tons of wood chips into $150 worth of mulch, he could have turned it into $3,000 worth of electricity. So hopefully we start, and so I can see, so right off the bat, I could become the middleman there, right? I say, hey, I'll buy your wood chips for $200. And then I go and sell it to some other guy for $1,000 a ton. I quintuple my money. He then makes electricity and triples his money. So that's perfect example of a fantastic payoff in renewable energy. I couldn't even believe the economics worked out that way, but they did. Okay, so these are your costs at the end of the day. And then we turn that into electricity. So you go from BTUs or megajoules, and you turn that into kilowatt hours per load. This might be what the utility is purchasing electricity for. So the utility is going to purchase it from a dam, purchase it from solar, purchase it from coal, purchase it from nuclear. So they're constantly buying energy based on availability and price. Put that to dollars per megajoule, and this is sort of what each load of wood would yield for electricity. You subtract and then there's some efficiency losses. This is the total amount of electricity made, and then finally what your net is if you're turning it into electricity. And then on this guy, I think I made an error here when I first submitted it, because the cost of natural gas, and this is something we should look into right now, because what you're going to want to do on your geothermal and on your wind is say, why would I go all this trouble to put in geothermal or wind when I can just buy natural gas to heat my house? Or I can just buy electrons to run my microwave. So we need to look at the cost of the conventional energy. So let's do that really quick, because I think I put in $10 per 100 cubic feet. So C being 100, CF being cubic feet, I think it's $1. So I think I was off by a more order of magnitude, and this number is therefore incorrect. And this is also a really good reason why it's a good idea to work with a team, because you got your buddy to check your work and you don't screw the thing up. So, but let's just go look. The units on natural gas get weird. Let's just pop out. So the EIA, it's a federally funded, transparent agency. Energy Information Administration. Okay. This is dollars per 1,000 cubic feet. So you hop out here. Okay. Now, here's your residential price. $9, $10, $12, $15, 16, etc. Man, it's really starting to go up. I don't think I've looked at this in a while. In fact, let's just take a peek at this. And so if we were, if we were wealthy men, we would be out there paying our statisticians to look at this data, and then paying our brokers to buy natural gas futures or sell natural gas futures. I mean, we would never touch, smell, or taste natural gas. We would just push a button and make a phone call and slosh our money around into different funds. But if you look, this right here was right around when, and this is for consumers, it's going to be different for industry. This is right around when that biomass boiler proposal was hitting pretty heavy at the U, 2007, 2008, 2009, because look what's going on. Up, oh man, more expensive. It peaks out right when they're about to pull the trigger on the project. Okay, not so much. So the price of natural gas, the fracking, et cetera, what have you, drove it down. And I'm surprised to see there's this much fluctuation, but it's cheapest in December. That is a little, That's more expensive in August. I do not know why. This is for residential. Now, it could be that the residential and the industrial are like 180 degrees out of phase with each other. I don't know. I do not know that much about it. But that is kind of intriguing. That's the first time I've seen that. Anyway, what I was going for there, guys, was just to say, okay, it's $10 per 1,000 cubic feet, and you can see what I did here. I made an error of 1 order of magnitude, and I said it's $10 per 100 cubic feet. So anyway, note to self, check your work. Okay, so that's where I wanted to go with that. So, basically getting your energy and your money talking to each other. So let's take a break, and then I'll look into a couple examples.